Hi everybody. In this video we're going to talk about the shapes of molecules, or what we call in chemistry molecular geometry. The good news is we don't have a whole lot of geometry that we have to remember, but it just tells us how the molecules are shaped. So normally in the classroom I simulate electron pair arrangements with balloons. And what the balloons represent are pairs of electrons. But we're just going to look at this with a simulating piece of software and do the best we can to understand what's going on since I'm not in front of you. So we need to think about what pairs of electrons do to other pairs of electrons. So if you think about the charges, what happens when you bring those charged particles close to each other? They repel each other because they have like charges. And so we know that the shapes are forced in the molecules because the pairs of electrons have that repelling force on each other. All right, so we need a little bit of terminology to get started. First, we have the bonds. We also call those bonding pairs of electrons or shared pairs. And then we have the dots. Those are called non-bonding pairs of electrons or lone pairs or unshared pairs. I tend to use shared and unshared pairs because that just makes sense to me. Also, probably just what I grew up with. So it's up to you what you call it. You'll see it different ways throughout the PowerPoint just to help you get used to it. All right, so go ahead and think about the formula for beryllium fluoride. It's an ionic compound. It should be BeF2. Go ahead and pause the video and draw its Lewis structure. All right, so you should have something that looks like this. And what we're looking at is just the central atom. So if you look, Be is our central atom, and we're looking at the shared pairs and the unshared pairs, so the bonds and the dots. If you look on Be, there are two bonds, so that would be two shared pairs, and there are no dots, so 0 unshared pairs. All right, and that is going to dictate the shape of this particular molecule. So when we look at that and we get that with the balloons, we find that it makes kind of a straight line. So it looks kind of like this. And I'll show you what that looks like in 3D in just a minute. So we call that shape linear. And the angle on that, those atoms of fluorine are about 180 degrees apart. Now I'm going to switch to JMOL. You can access this through PowerSchool Learning. It's under the meme in Unit 5, and you can click on these and manipulate these shapes yourself. Okay, so when you get in there, you want to click on the VSEPR, we call that VSEPR, and this is the linear shape. We're not using CO2, but it's going to behave the same way. So you can see with these, there's the central atom, and there are the other atoms on the end, and you can see that they actually form a line. And if you kind of click on this and drag it around, you can play with the shape and get a 3D picture or 3D view of how this looks. So try to take some time and do that and see what you think about it. Okay? So let's get back to our PowerPoint. So the two shared and 0 unshared pairs will always form a linear shape. Okay, and that's what your Lewis structure looks like, and also how we would draw it in 3D. We're not going to focus on how to draw it in 3D today. I'm just going to skip over that part of the PowerPoint, so just bear with me. All right, so again, formula for boron trihydride, draw the Lewis structure, pause and draw, and then come back and we'll talk through this one. All right, so you should have a Lewis structure that looks like this. Remember that hydrogen only can have 2 electrons to have a full fake octet. You can kind of imagine me making the little finger quotes, the full octet. So if you look again on the central atom, remember boron is our central atom. There are 1, 2, 3 bonding or shared pairs, and there are no dots, so 0 non-bonding pairs. And if you look, that shape is a little bit triangular, and so we call this one trigonal planar. And if you look, those are pretty evenly spaced around the boron, those hydrogens are. And so those are about 120 degrees apart. And if you're having trouble visualizing it, imagine that if you had a circle drawn that touched all 3 of those hydrogens, and divided it evenly into 3 parts, they would each have 120 degrees. I'm not going to test you or quiz you on the angles. Just want you to be aware of what they look like. All right, and this would also be not only the Lewis structure, but the 3D drawing of boron trihydride. All right, now let's look at sulfur dioxide. Go ahead and again draw the Lewis structure, pause and draw the Lewis structure, and then we'll come back to this. All right, so you should have gotten a double bond. This is new. And then we also have an unshared pair that we're going to have to deal with. So think about, you have this double bond. Those electrons are repelling each other, but they're in that same little space between oxygen and sulfur. So we count those as one shared pair, even though there are 2 pairs of electrons there. And the same for a triple bond, only count it as one shared pair. So here we count that as this would be 2 shared pairs. And then if you look on this central atom, you can see that there is 1 unshared pair. All right. So we've got this shared pair that's a double bond, and then another shared pair, and then an unshared pair. So we only count double and triple bonds as 1 shared pair, and then we've got those new unpaired electrons there. So now we've got 2 shared pairs that are adjusted because it's a double bond, and then 1 lone pair or unshared pair. All right, we can't see that unshared pair. There's no atom hooked to that unshared pair of electrons, but it is still repelling those electrons in the bonds, and so it's forcing this bond, this double bond, and this single bond closer together, because this is still pushing down, it's repelling those electrons. So what it really looks like in 3D is this. It's got the same about 120 degree angle, because you've got this pair of electrons here, you've got 2 pair here and 2 pair here. And we call this shape bent. And again, they're about 120 degrees apart. So it's like you have this shape that we looked at before, where you had the 3 bonds, but we removed that atom. Okay, so that pair of electrons, even though it is not bonded to an atom, still causing repulsions. All right, again, pause and draw the Lewis structure for silicon tetrafluoride. All right, so you should have something that looks like this. Again, remember, we only are interested in the central atom. So we have 1, 2, 3, 4 shared pairs, and no dots, so 0 lone or unshared pairs. And this one, it gets a little dicey because they're not spread out as far as they can be if you. So the way that we would describe this shape would be tetrahedral. And I want to show you this one in JMOL, and I'll encourage you to think about clicking into JMOL. So I'm going to show you, this is methane here, and you can see that these are not just in 3 dimensions, they're in 4. And you can see these are not just in 2 dimensions, they're in 3. So they're not just in the plane of the screen, but also coming towards you and coming away from you. And I'm going to spin this way so you can kind of see. If you look, there's one going up, one going down at about 109 degree angle, one coming towards you from the screen, and then one going away from you into the screen. So that might help you kind of visualize the whole shape of it. We call this tetrahedral. If you could imagine that shape had sides, it would have 4 sides, and they're about 109.5 degrees apart. Remember, tetra means 4, so it's a 4-sided figure. Now, normally I would make you learn how to draw this in 3D, but I think it's really hard without being able to visualize it. Now let's look at ammonia. So remember the formula for ammonia. Go ahead and pause and draw the Lewis structure. All right, so you should have something that looks like this. Count the shared and unshared or bonding and non-bonding pairs. You should have 3 bonding or shared pairs and 1 non-bonding pair. So with that, again, this non-bonding or unshared pair still has the same effect. So it's kind of like this tetrahedral shape, except we've removed an atom from it. And so I'm going to show you what that looks like. It's kind of like a little pyramid or a tripod. So here is the trigonal pyramidal shape, and you can see that this is different from the trigonal planar, and I'll show you that one. You can see that it's shaped like a little tripod, so it doesn't lay flat. Trigonal planar molecules, they are actually flat. All of the atoms line up in the same plane. So you can see that that's a much different look. So trigonal planar, you can see all the atoms are in the same plane, the central atom and the atoms on the ends of the bonds. With trigonal pyramidal, you can see that these are not all in the same plane. Okay, and again, we're not going to worry about this 3D shape. Just know that if you have a shape that has 3 shared pairs and 1 unshared pair, then that means it's going to have the trigonal pyramidal shape. And you will need to know those. You'll need to know the names of the shapes and the number of shared and unshared pairs to determine which shape each molecule has. Go ahead and pause and draw the Lewis structure for water. All right, so you should have something that looks like this. Look at that central atom. You've got 2 shared pairs and 2 unshared pairs. And if you put those together, it looks like a bent shape. Now, this is not the exact same bent as the one that we saw earlier. The angle is a little bit smaller, 109.5 degrees compared to 120, but we don't differentiate between that in this class. So we just call it bent and go with it. All right. And if you look at that in JMOL, there's water, and you can see that it's bent. All right. And then we're going to deal with those expanded octets. So remember that certain elements, phosphorus, sulfur, arsenic, selenium, antimony, tellurium, those elements can have bonds that form down in those d orbitals. So just be aware that if I tell you there are 5 or 6 of something that hook onto that central atom, just go for it. Just hook them all on there. All right, so stop and draw the Lewis structure for phosphorus pentafluoride. So yours probably looks something like this. And again, we're looking at our central atom. So we've got our P, and that has 5 shared and 0 unshared pairs. Remember, we're only looking at everything around the phosphorus. And so the way that that looks, we call that one trigonal bipyramidal. And let me show you what that looks like here. So trigonal bipyramidal would be something like this. And you can see that 2 of the atoms are directly across from each other. So those with the ones on the side make 90-degree angles. But then if I spin it this way, you can see that these 3 that are around the center are at 120 degrees. So it's a little bit different. All right. And then try again to pause and draw the Lewis structure for sulfur hexafluoride. All right, so that looks like this. Sometimes people say, oh, it looks like a little flower or a star. But if you look at sulfur, the central atom, we have on there 6 shared pairs, no lone or unshared pairs. And so the way that it arranges itself, we call this octahedral. And octa, because the shape is like what we call an octahedron, an 8-sided shape. So it's kind of almost like a diamond, kind of pointed on each end. And those are all 90 degrees apart. So let me show you that one in JMOL. So that would be this one, okay? So you can see no matter which way we spin this thing around, these are all 90 degrees. So it's similar to the trigonal bipyramidal, except that all these angles are 90 degrees instead of having those 120-degree angles. If you ever played with jacks when you were little, this is the shape of a jack. If you've ever stepped on a jack, that's painful. All right, and this is how we would draw it in 3D. just in case you're interested. I'm not going to hold you responsible for that. All right, so we call this VSEPR theory, and I know it's spelled VSEPR, but we call this VSEPR theory. It's valence shell electron pair repulsion. And basically what it says is that electron pairs try to get as far away from each other as possible, and that's how the shapes of the molecules form. If you have questions, remember to get in touch. I'm happy to help you. Hope you're doing well. Take care.